Hi, welcome to this lesson of linear transformation. Okay, so this another theorem I want us to write a proof to. Then we're going to use all the three theorems and their proofs to solve examples. Okay, um, let V and W be finite dimensional vector spaces of equal dimensions. This should be very important. These are equal dimensions, so it means that the dimension of V is equal to dimension of W, right? And let T such that V maps to W be linear, then the following are equivalent. Um, T is 1 to 1, T is on to, rank of T is equal to dimension of V. What it means is that to prove this, to prove equivalence, we have to show that if T is 1 to 1, then it will imply that T is on to. If T is on to, then it will imply that rank of T is equal to, and if the rank of T is equal to the dimension of V, then it will also imply that, so this also imply this, right? And at the end of the day, it means that any one of them implies the other, right? So if you're able to prove this chain, that we want to prove that A implies B, and B implies C, and C will imply A, right? It's like a chain. A will imply B, B will imply C, C will imply A. It means that B will imply A, right? C will also imply B because C implies A and A implies. So it's like that. Either two of them or every two of them will imply each other. So A implies B, B implies A, B implies C, C implies A from the chain that we have here. Okay. The part I'm saying that B implies A is because B will imply C and C will imply A. And if B is implying C and C is implying A, it means B implies A, right? So I mean that's what I want us to do. I want to prove first A implies B, right? Let's go back to what we have. We know that T, right, T maps to W, right? And the dimension of V is equal to dimension of W, right? How do I start this? From one theorem we said from the dimension theorem. Dimension theorem. What can I say? We know that the nullity of T, right, which is the dimension of the null space of V, right, plus the rank of T is equal to the dimension of V, right? We know this from the rank nullity theorem. Now, what is the nullity of T, which is the dimension of the null space of V? What is it, right? It's equal to the dimension of. Now, what is the null space of T? Remember, the A is saying that T is 1 to 1, and from another theorem, right? From another theorem we proved in one of our videos, if T is 1 to 1, the only case T will be 1 to 1 is that, so A means that A will mean that the null space of T, if T is 1 to 1, then it means the null space of T is equal to just the zero vector. And what is the dimension of a vector that consists of only the zero vector? The dimension here is 0. That's one thing you should also know. The dimension of a vector that consists of only, or vector space that consists of only the zero vector is 0, right? And so it means that from our rank nullity theorem, we're going to have 0 plus the rank of T is equal to the dimension of V, right? What is the rank of T? The rank of T is the dimension of the range of T. And what is that equal to? The dimension of V, where we know that V and W have equal dimensions. So this is equal to the dimension of W. And what is the range though? So what is an onto function? Something is onto, right, if the codomain here, right, is equal to the range. So if the codomain, what I mean by the codomain is, we know that this is V, this is W, right? and if V comes to W, W will become the codomain, the set where you should get something from. But if it happens that all your sets you get in W is the same thing as, all the range, all the range, the total range you get is the same thing as the codomain, then you have an onto function, right, or onto map. Okay, so since that the dimension of the range of T is the same thing as the dimension of W, which is, here is the codomain, it means that, so this implies that we have T is onto, because the range of T is the same thing as the dimension of the codomain, right? All the time, if you remember, we know from our previous lessons that the range of T is a subset of W, right? But here we are saying that the dimension of range of T is the same as the dimension of W. It means that they are the same, right? And it means T is onto. Now let's look at B implies C. If T is onto, what can I say? Then the rank of T is equal to the dimension of W, right? And the dimension of W is what? The same thing as the dimension of V, and that part is proved. B implying C, C is this. Rank of T is equal to the dimension of V, right? And from the theorem, it was stated that the dimension of V is equal to the dimension of W. And so if T is onto, then it means the rank of T is the same as the dimension of W, which is the same as the dimension of V. So it means that the rank of T is indeed the dimension of V. Now C implies A. I want to show that if rank of T is equal to dimension of V, then what can we say? We want to show that the function or the transformation is 1-to-1, right? From, again, if rank of T is equal to dimension of V, it means that we have the nullity of T to be equal to 0, because from the rank nullity theorem that we did earlier, we said that the dimension of, or the nullity of T plus the rank of T is equal to the dimension of V. So if the rank of T is equal to the dimension of V, it means the nullity of T is equal to 0. And in that case, it means that the null space of T is just the 0 vector. From our previous video, we said that if the null space of T is just a 0 vector, it means T is 1-to-1. And that ends this proof as well. So that is the proof to this theorem here, stating that if V and W have the same dimension and T maps to W is linear, then these following are equivalent. Okay, so we are having a very solid foundation now in this linear transformation lesson. We're going to pick more advanced problems, examples to solve to clarify all these theorems. And when we are done, we can write advanced problems, like advanced proofs using all these theorems. So see you in our next discussion.